I 3D printed 180 of these calibration cubes on my 3D printer to answer one question. Which 3D printer nozzle diameter is the most dimensionally accurate? I'm not talking about fine details in the print or surface finish. I'm talking about dimensional accuracy. These 3D printing calibration cubes are nominally 20 millimeters by 20 millimeters by 20 millimeters in the X, Y, and Z, and are used to check how well your 3D printer is printing. And people use them to make tweaks and adjustments to their 3D printer to get them to print as capable as they are. So I took my nozzles and printed a 0.6 millimeter, 0.4 millimeter, and 0.25 millimeter calibration cube. Now, any experienced 3D printer will tell you that the larger in diameter your nozzles get, the less detail you get on the surface. So if we look at this calibration cube printed in a 0.6 millimeter nozzle, you'll see that the edges are rounded. There are visible large layer lines on the top surface, and also the layer lines on the side are larger than, say, on this 0.4 millimeter cube, where the edges are a little bit more rounded, the layer lines less visible, and the surface finish looks a little bit better. 0.4 millimeter is pretty standard, but if you want more sharp detail than that, you'll use something like this 0.25 millimeter nozzle or a 0.2 millimeter nozzle. My machine in particular is made for a 0.25 millimeter nozzle, and we'll talk a little bit more about that later. But as you can see on the smaller diameter nozzle, the layer lines less visible, sharper detail, so that means it's going to be the most dimensionally accurate, right? And that's the question I've set up to find out. So in this video, we're going to be using our FlashForge Adventurer 5M 3D printer and doing a statistical capability study on these different nozzles to see which one has the greatest dimensional capability. Meaning, statistically speaking, which diameter nozzle is capable of printing to the 20 millimeter nominal size on the X, Y, and Z axis the most consistently. So for this video, I'm going to be using Orca Slicer set to all of the default settings for the 0.25 millimeter nozzle on the FlashForge Adventurer 5M 3D printer. And that's just what I'm showing here, all the default settings for this particular nozzle and this particular printer and this particular filament in Orca Slicer. Now these settings are going to vary by printer, by filament, by slicer, by nozzle diameter for any different type of 3D printer, and just for this project we're going to be using the defaults for these different nozzle sizes in Orca for the FlashForge Adventurer 5M. If this video does well, in the future I may do a video talking about how tweaking these different settings can affect the dimensional capability of the printer in these particular filament. But for now we're sticking to the defaults and just running with that. So there were a number of parameters I did have to change depending on the nozzle thickness, being the number of walls and the layer height. Recommended layer height's 50% of the nozzle diameter, and the wall count I changed to target a thickness of 1.2 millimeters, so that works out for 5 walls for the 0.25, 3 walls for the 0.4, and 2 walls for the 0.6. And then the layer height is just 50% of the nozzle diameter, so 0.3 for the 0.6, 0.2 for the 0.4, and 0.125 for the 2.5. And the other thing I did, which is different than standard, is set my G-code up for automatic printing. If you don't know how to do that, it's pretty simple. You open up the G-code file in a text editor, copy all the G-code for printing whatever you're printing, and then add a couple of G-code moves in for the printer head to sweep the bed and knock the object that you're printing off the build plate. Doing this allows me to print 30 each of these cubes for each filament and each nozzle diameter much easier, because I don't have to babysit the printer over what could end up being a 15-hour period and just keeping the printer going. It's just set up to do it automatically. And doing it this way, I think, did have some effect on my Z height capability, which we'll see later in the video. But we'll talk through that and what those numbers show us when we get there. And with that, I sliced up all my files, edited all my G-code, and I was on my way to 3D print. And this 3D printer is an absolute workhorse. This is what I've been doing a lot of my 3D printing for my molds on. The FlashForge Adventurer 5M. It is easily, right now, the best entry-level 3D printer, dollar for dollar, on the market. It's not even close if you ask me. This is a Core XY 3D printer capable of printing at 300 millimeters a second travel speed. PLA, PETG, I've printed PETCF on it. You could do an enclosure, print nylons, ABS, ASA, all those fancy engineering grade filaments on this printer. Automatic bed leveling, temperature calibration, vibration calibration, the whole 9 yards. This thing is great. And at $300 US, it's not that much more expensive than an Ender 3, the current generation Ender 3s, and you get so much more for your money. It's just a phenomenal printer. I love this thing. And as we'll see later in this video, this thing is capable of holding some ridiculous tolerances with the right nozzle and printer filament. And again, since this is different than my normal content with the 3D printed molds, I may be able to do a comparison of this printer versus my Bamboo Labs X1C if you guys are interested in that. The reason I'm doing this type of content is I'm trying to find some content that's I'm able to do over the winter when I can't go fishing. So I'm going to focus on 3D printing content for a little bit. And as you can see, we just did that auto clear and reprint cycle we set up in the G-code right there. And if you 3D print a lot, you're thinking, oh wow, that's going really fast for a first layer. Yes, it is. I had to go back and reset that, but I didn't want to take another video since I already had this one. And through the magic of YouTube video editing, just like that, I had 0.6, 0.4, and 0.25 millimeter cubes, 30 each, printed up and ready to go. And if you're wondering why I went through all the trouble to print out 30 pieces for each nozzle diameter, if you've ever heard of Six Sigma in a manufacturing environment, that's why. We'll talk more about it later, but basically 30 pieces is the minimum data size you need to get statistically meaningful data out of any data set. So at this point, having 90 PLA plus cubes, I started measuring and recording my results. And this video is a little misleading. I was going diagonally across the face, but just for the sake of the video, just something to show like there. Except I didn't stop there, because I printed 30 each in 0.6, 0.4, and 0.25 in PETG filament, because I wanted to see if the results we got in PLA were also true in a different filament, this case PETG. And if you're wondering specifically what brands of filament I was using for these tests, the PLA was Sunlu PLA Plus white filament, and the PETG is Kingroon black PETG. These are both fairly cheap Chinese manufactured filaments available on Amazon for, I'll say, bottom of the barrel prices. There are cheaper filaments, but they're not cheaper by much. These filaments are generally regarded as, I'll say, bargain value filaments, and I could use this same statistical analysis we're going to go through on more expensive filaments to see if there's any value in buying the more expensive filament. Looking at our 0.6 nozzle with Sunlu PLA white filament, you can see I've broken up the measurements into the X, Y, and Z axis of the calibration cubes and reported my measured values with my calipers for all 30 cubes in these 3 different axes. And then I calculated my average, standard deviation, and normal distribution of the individual axis based on my measured data. For those of you who are not so familiar with the metric system and more familiar with imperial, one, get familiar with the metric system. It's superior to the imperial system in every way. And remember that for every 0.0254 millimeter is 1/1000th of an inch. For context, a single sheet of regular computer paper is about 4/1000ths or 0.1 millimeter. And now that we've got the metric system out of the way, let's talk statistics. What I've done here is plot a normal distribution bell curve for each axis of the calibration cubes and plotted the 1, 2, and 3 sigma measurements based on our standard deviation of our data set. So what does that mean? For 3 sigma above and below the average of the data set, you are going to capture 99.72% of the values in an expected data set. So if your sample population is 30 pieces and you have a larger population of, say, 1,000,000 pieces, you can expect your measured value on those 30 pieces to represent 99.72% of the population of a 1,000,000 piece data set. What that means is that if I were to print 1,000,000 of these calibration cubes, I could expect 99.72% of those calibration cubes to fall inside of this range for the measured values along the x-axis. For 1,000,000 calibration cubes with a 0.6 millimeter nozzle and PLA plus white Sunlu, I could expect 99.72% of 1,000,000 cubes to fall in this range of measured values. The same is true for these values in the Z. And then what you can do is, based on that set of data, you can say that the 3D printer with this filament and this nozzle is capable, statistically capable, of holding a just over 5/1000ths of an inch tolerance window off of the average value that it's printed. So in this case, our x-axis average of the calibration cube is 19.9 millimeters. and I could expect the 3D printer to hold that value average in a 0.13 millimeter window, half of the window above, half of the window below the average, 99.72% of the time over a million pieces. It's really over X number of pieces, not necessarily a million, but a million is the standard number you'll hear talk about in a Six Sigma capability context within industrial manufacturing. You'll hear about parts per million or defects per million in this type of context. In a manufacturing context, you'll also hear the term CPK and PPK thrown out in these types of discussions. But for this study and this data, I don't have a assigned tolerance window that I'm trying to hit. I'm really more interested in that tolerance window the printer is capable of holding. The reason for that being, I know my X average and my Y average are both a little bit shy of the 20 millimeters. There are things I can do in the slicer settings that can adjust that to get those average values onto nominal. So the average that I'm hitting doesn't necessarily matter because you can tweak your 3D printer in to hit that average right on the nominal. What really matters in this context is how close to that average over a theoretical million times you're going to be. So what we're really doing is measuring with this 0.6 millimeter nozzle and this 3D printer and this 3D printer filament, how consistent to itself is it? And in this example, in the x-axis, it's consistent to itself in a window of about 5 thousandths dimensionally. And in the y, about 7.5 thou, and in the z, just shy of 5 thousandths. That's what these numbers mean. And if we come down here and look at our bell curves, what I've done is laid over a 1 sigma, 2 sigma, and 3 sigma band centered on the average with the percentages up here so you guys can understand. And for this example, this from here to here underneath the bell curve is going to be 34.13% of our data on a normally distributed bell curve. And then if you come all the way out to here in this range underneath the curve, you're going to have just over 13.5% of your data. So again, we're measuring how consistent to itself is this filament with this nozzle and this 3D printer. And you can see here our X, Y, and Z normal distributions are fairly well centered actually on the average and evenly distributed, which basically means there's nothing skewing the data set one way or the other. So to answer the question then of which nozzle is most accurate, we can see that our 0.6 millimeter nozzle with the PLA Plus is capable within 5 thousandths in the X, 7.5 thousandths in the Y, and just under 5 thousandths in the Z. Well, what about our 0.4 nozzle? Our 0.4 nozzle is capable with PLA Plus, Sunlu PLA Plus, to a tolerance window of 2.5 thousandths in the X, just under 3 thousandths in the Y, and just shy of 4 thousandths in the Z. And we can see our averages are much closer to the 20 millimeter nominal value than the 0.6. So this is all to say that the 0.4 millimeter nozzle is more dimensionally stable statistically than the 0.6 millimeter nozzle, and it is closer to the expected nominal values than the 0.6 millimeter nozzle, which you might expect because it's a smaller nozzle diameter, the standard nozzle size. So what about the the smaller 0.25 millimeter nozzle? Well, we can see that in the X, we're capable within a 2.5 thousandths window, a 3, call it 3 thou and 2 tenths, 3.2 thousandths of an inch window in the Y, and just over a 4 thousandths capability in the Z, which is very similar to the 0.4 millimeter nozzle. But if you look at the X, Y, and Z averages, you'll see that the X and Y average are actually further away off nominal than the 0.4. And as I was saying earlier, there are things you can do in the slicer to account for that won't really matter. So in the grand scheme of things, the dimensional capability of the 0.4 and the 0.25 millimeter nozzles are more or less the same, specifically with PLA+, but we can see that the 0.6 millimeter nozzle performs worse than the 0.4 and 0.2. Because the 0.4 millimeter nozzle happened to just land on the nominal values with the default settings, right now I'm going to say the 0.4 millimeter nozzle, at least for the PLA, is the winner. But that begs the question, what about a different filament, PETG? Let's take a look. With the 0.6 millimeter nozzle, we have a capability in the X of 0.38 thousandths. I'm sorry, 3.8 thousandths of an inch in the X, 0.0053 in the Y, and just shy of 5 thousandths in the Z. If we go back to 0.6 in the PLA+, you'll see that looks like we're a little bit better in the X and Y with PETG in 0.6 than we are in PLA. The Z is actually exactly the same. Look at that. So does that mean PETG is going to be a more accurate filament than the PLA+? Well, let's take a look. If we go to 0.4, you have a capability of just over 4 thousandths in the X, almost 8 thousandths in the Y, and almost, call it 16 and a half thousandths in the Z. And there's a reason for that we'll talk about later, where that Z is looking pretty bad. It has to do with the automatic print settings. But look at that Y. It's almost 8 thousandths. But our X is actually pretty right in the middle, right in between our X and Y with the 0.4 nozzle, or I'm sorry, the X with the 0.4 nozzle is right in between the capability of the 0.6 nozzle, so pretty close. We don't see a big shift in greater accuracy from the 0.6 to the 0.4 like we did with the PLA, which I have down here. So then let's look at the 0.25 nozzle. Looking at the capability here, and the X and Y, you're looking at, again, right at 4/1000ths of an inch, just above, which falls right in line with the X on the 0.6 in PETG and the X in the 0.4 in PETG, which is telling me the nozzle diameter with PETG, at least the specific brand of PETG, does not matter as much as it does in the PLA Plus, which is interesting. Even the Y on the 0.6 PETG still fairly close to the capability with the 0.25 in PETG. So we can conclude Sunlu PLA Plus is more dimensionally capable than Kingroon PETG, just by nature of the two filaments. We can also conclude that the nozzle diameter matters less in PETG than it does in PLA Plus for dimensional capability, at least with these two filaments. And we can also conclude that the 0.25 and 0.4 nozzles are roughly the same capability in PLA Plus, with 0.6 having a noticeable decrease in the capability. So there we have it, 0.4, 0.25, best for PLA. Doesn't matter so much in PETG, at least with these two specific brands of filament. So getting back to the z-axis capability and why that graph is skewed to the right and the capability is not that great in the z-axis on the PETG. So I found that the bed adhesion on the PETG was so great when the printer head was going to sweep the cube off the bed. Sometimes it was actually breaking at the layer 9 and not clearing the cube entirely off the print bed, which resulted in it trying to print over top of material that was already there. I thought I kicked all these cubes out and reprinted them when I was going through and remeasuring, but looks like I was still having some trouble in the capability of the z-axis, even though I didn't notice it by hand, which I think goes to show just how powerful this capability study analysis and the statistical data is. And with that, this has been 3dprintandmolds.com. If you're new to the channel, I 3D print and design my own custom fishing lure molds for soft plastics. This is a little bit different than the content I've been posting over the summer, just because now we're into the fall, getting into the winter time. Those fish aren't going to be swimming around the same areas they were before, which makes it harder for me to fish and catch them. Just trying out some new different content, so let me know what you guys think, and thanks for watching.